So we're still working through more examples of separable differential equations. We're on page 606 in the workbook now. So let's take a look at the next problem we've got, which is a little bit trickier, but it's the same basic ideas. So here we've got in problem number 5, we have dy dx is equal to x to the fourth times y minus 2. So we're going to do the same thing we did before, except it's not going to be cross multiplying. We're going to multiply dx to get it over to this side, and then we've got to divide both sides by y minus 2 to get the y minus 2 over here. And when we do both of those things and separate the variables, we get 1 over y minus 2 dy is equal to x to the fourth dx. So integrating this looks pretty easy. Integrating this one looks a little bit trickier. So I want to start off differentiating this by introducing a variable substitution. I want to do a u substitution. So u is equal to that y minus 2. And that means that du is just equal to dy. And when I do that, this side of the equation turns into 1 minus u du is equal to x to the fourth dx. Well, finding the indefinite integral of this side is the same thing we've been used to. So what's that equal to? That's equal to 1/5 x to the fifth. Over here, now that we've done this substitution, we've got 1 over u du. So this isn't something where we can use the power rule, but we do know what the antiderivative of 1 over u is. Check your reference sheet if you don't remember it. Well, 1 over u is the natural logarithm of the absolute value of u. And then we'll just add a plus c over here. And now I'm going to substitute the y minus 2 back in here. The natural logarithm of y minus 2 is equal to 1/5 x to the fifth power plus c. And at this point, why don't I substitute in my values? So I've got that x equals 0 and y equals 0. So this is the natural logarithm of y minus 2. So that's 0 minus 2. So that's negative 2. The absolute value of negative 2 is positive 2. So this is the natural logarithm of 2. These absolute value symbols were really important because natural logarithms of negative numbers don't exist. So if I was trying to calculate the natural logarithm of negative 2, I'd get into a whole lot of trouble. And over on this side of the equation, x is equal to 0. So 1/5 x to the fifth is 0. And so I've just got c over here. So c is equal to the natural logarithm of 2. So if I wanted to be super cautious, I could just express the function like this, x to the fifth plus the natural logarithm of 2. But if I wanted to turn this into something that was a little bit more recognizable, what I could do is I could raise e to both sides of this equation. All right, and let's do a little bit of exponential things. So remember that the exponential function and the natural logarithm are inverses of each other. So the exponential of the natural logarithm of y minus 2 is equal to the absolute value of y minus 2 on this side. All right, and over here, I've got e raised to the power of 1/5 times x to the fifth plus the natural logarithm of 2. But remember, adding logarithms is the same as multiplying this times e to the natural logarithm of 2, right? I'm multiplying these two things with the same bases, so that's just a matter of adding their exponents, just like what I have here. And I can't make this any simpler than it is, but I can replace this, because that's just equal to 2 again, because e and the natural logarithm are inverses of each other. So that's 2 times e to the 1/5 x to the fifth power. So you could write it either one of these ways. This way is prettier, but it's more work, and there's always a chance you're going to make a mistake somewhere along the way. So if all they're asking for is an equation in terms of x and y that satisfies both of these equations, you can always just stop here if you wanted to. All right, but I wanted to show you how you can how you can transfer natural logarithm statements into statements involving exponents. All right, so in the next video, we'll take a look at the last problem here, and I have a feeling that they might be tossing a few more quirks our way. So let's see what that looks like when we get there.